Okay, we're live. So whenever you're ready.
Sounds good. Let me share my screen. And get started, Rex. So hi, everyone. Welcome back to this series of lectures on the statistical mechanics of disordered systems. So let me start by reminding ourselves what we're doing. So we are studying this model of statistical inference where we observe a noisy version of a rank 1 matrix, this x bar transpose. It's a vector of length n, and we let n go to infinity. And we try to discover the behavior of the minimal mean square error, or quantities of this type. And the way we're going to achieve this is, as for Convex, we're studying something analogous to a free energy, and we hope to identify the limit of this free energy by describing it in terms of a Hamilton-Jacobi equation. And once we have done that, we can understand the limit of the minimal mean square error by just studying the derivatives of this object. So last time, what we have done is give a proof of this theorem, which is displayed on the first two lines. And this theorem states an approximate version of the equation we want to identify when n goes to infinity. So it tells us that while it is not exactly true that this relationship between the derivatives is zero, it looks promising. It looks like there's a good chance that it's going to go to zero as n goes to infinity. Partly because, okay, the first term is 1 over n times something, and this sort of term we are used to also from our study of Convex. And the kind of novelty is that there's this extra term which speaks about the size of the fluctuations of Fn, the free energy Fn. And this I discussed briefly last time and said, this is a quote unquote classical thing that one can do. It's called concentration result. So concentration comes from the fact you're saying that some random variable is concentrated around its mean. And so in the problem set number 9, I propose a step-by-step way to derive some concentration result, not the optimal one, but something that will be sufficient for our purposes. And the concentration result that we get from there is that this difference between Fn and Fn bar is bounded by some constant over n to the 1/3. So anything that goes to 0 would be fine for me. Okay, so yeah, I did not emphasize this, but another difference with Convex is, of course, that the free energy Fn is random, and so we have Fn and we have Fn bar. Okay, and so this equation is for Fn bar, and we're going to try to find an equation for Fn bar. But as we see from this display, Fn is close to Fn bar. So there's a question in the chat. The limits. So this, I don't know. So yeah, that's a good question. I don't know what will be the limit. So maybe you can hope to prove a CLT, but maybe without the supremum. With the supremum, I suppose that if you just rescale this, so there's a square, so you have to rescale by n, and I suppose this will still diverge because you have a supremum here. So if you remove the supremum, then maybe you can prove it without the square it converges to a Gaussian, but this I'm not sure how to. At least I haven't thought about it carefully. Maybe some people have. Yeah, it may have been proved actually. There's a paper, I think. Yeah. Okay. So maybe this has been proved actually, at least in some regimes. Okay. So one last thing I want to. So now what I want to do today is complete the arguments, really explain how we go from this to saying that indeed, as n goes to infinity, Fn bar converges to the solution of the partial differential equation. And so I will have to explain how we deal with this. And there's some subtlety that comes from the fact that the concentration we have is for Fn, but the error term that is on display in the inequality is for the derivatives of Fn. And one of the tools we're going to use in order to get control of this is the fact that Fn bar is convex. So we've seen that last time. And in fact, I also would like to say that Fn is kind of convex. So it's not true that Fn is convex, but it's almost true. And I'm going to explain exactly what I mean by this. So last time, you may or may not remember, but if you don't remember, it's okay. I'm going to recall it here. We computed the second derivative of Fn. And we found that it is the variance of this quantity we denoted Hn prime last time. And there was some correction term which had this form. Okay, and maybe we can massage this term further if we further take the expectation. But here I don't want to do that. Okay, I just want to speak about Fn. And what I want to record is that, well, if it were not for this spurious term, this quantity would this calculation would tell us that the function is convex in H, okay, because this is the first term is non-negative clearly. And in terms of order of magnitude, actually this term can be very big. Can be Hn can be of order n, so this can be of order n squared. On the other hand, so there is this guy which we don't know its sign, but this one is of order 1. So up to an order 1 correction, in fact, we know that Fn is convex. Yeah, and this is what I want to remember. Yeah, I want to remember that. So if I remember also that the norm of x is bounded by square root of n, what I want to observe here is that the second derivative of Fn is not non-negative, but is bounded from below by the norm of z divided by square root of n times this 2h to the 3 halves. Okay, and the norm of z is approximately of order square root of n. It's a random variable, but its order of magnitude is square root of n. Okay, if you compute the second moment, you will see that this is true. Okay, so this will be an ingredient in what we're going to do. So now what I want to do is rely again on this convex selection principle. So we're going to touch the function Fn bar from above by a smooth function and try to verify that at the contact point and in the limit of large n, the derivatives actually do satisfy the equation. Okay, so let me write this down. So theorem. Oops. Okay, so maybe I should have said it earlier. So it's also true that Fn bar is uniformly Lipschitz. Okay, when we express the derivatives, it's easy to see that they are always bounded by 1. Okay, so just as for Curie-Weiss, it's clear that by Arzola-Ascoli, we can this sequence Fn bar is pre-compact. Okay, we can extract converging subsequences. So I'm going to talk about one possible subsequential limit. I'll call it F. And I'm going to now look at the contact point. So let P and H positive. I'm going to assume it's strictly positive, but I don't want to be at the boundary. Okay, so there's a question in the chat about the last inequality I wrote down. It's just I apply Cauchy-Schwarz in this guy, okay? And the norm of X is bounded by square root of n. And Z is not being averaged over in the bracket. So I just put it up. Okay, so I take a contact point, I detach it from 0, and I take a smooth function. And we assume that indeed we are touching F from above. And we, for convenience, I'm going to say it's strict local maximum. Okay, and if this happens, then I claim that it must be that the derivatives of the test function satisfy the equation. Okay, this is exactly what we need in order to apply our convex selection principle. Okay, so that's what I want to prove. Is it clear? Are there further questions? Okay, so let's move to the proof. So I'm going to ignore, I'm not going to denote explicitly the subsequence. Okay, I'm going to just pretend that it's actually converging without taking subsequence, just for convenience of notation. And as we have discussed several times already, if we have this thing converging to F, and we have this strict local maximum for F minus phi, we can find a sequence of points. Let's call them Tn Hn, such that Fn bar minus phi has a local maximum. Okay, so and Tn Hn converges to Th. So oops. So let Th positive and phi in C infinity be as in the statement. There exists Tn Hn converging to Th such that Fn bar minus phi has a local maximum at Tn Hn. Okay, and what I want to do is try to control these guys on the right hand side in this inequality. Okay, I want to control these guys. So in fact, my job is already kind of done for the second order term, because as we have already seen in the proof of the standard Curie-Weiss thing, this will imply that the second derivative of Fn bar minus phi at Tn Hn is non-positive. So in particular, it gives us an upper bound on the second derivative of Fn bar. Okay, and what I want to do, so it will be convenient for the first term, but in order to understand the second term, I want to be just a little bit more precise about this fact. Okay, I want to, instead of saying this at some sort of extremely microscopic level, just controlling the second derivative of Fn bar, I want to say that I can, in some sense, Taylor expand Fn bar in a way which is consistent with the fact that the second derivative is bounded, and in the neighborhood which is of a size which does not depend on n. Okay, it's just a slight refinement of the statement that the second derivative is bounded. Okay, so let me make this more specific. So we first show that, so it's something that I could call a C11 estimate locally at the contact point. So, and if this name doesn't talk to you, let's just forget about it. It's just a name again. For every h prime smaller than. Okay, so for convenience, I'm going to use C to denote some constant, which may vary from place to place. Okay, so there exists, I should write everywhere, there exists a constant C such that blah, blah, blah. And I think of C as being very large. So here I'm saying for every h prime sufficiently small, I want the following to be valid. So I'm writing a Taylor expansion of Fn bar near the contact point. Okay, so I hope that this makes sense. It's saying that it relates to the fact that the second derivative is bounded, right? Because at least the fact that the second derivative of Fn bar is bounded is a consequence of this estimate because there is this C here. Okay? And okay, this part is clear because the function is convex. Okay, so the function is always above its tangent. So this is by convexity. Okay, so what I need to justify is this part. So I'm going to do this. And well, I call this a Taylor expansion, but in fact, I'm going to use, oh yes, thanks for the comments. It's indeed H prime here on the right. Absolutely right. Thanks a lot. Okay, so I'm going to rely on the, let's say, an exact Taylor expansion to prove this. So by I don't know, Taylor expansion with remainder. Or by Taylor's formula, I should call maybe. Okay. We can give an explicit form for this remainder. This. And it has the following form. Okay, and now I want to use that. So you remember when we have this Fn bar minus phi has a local maximum, I often do this drawing in the margin. So this would be Fn bar and this would be phi to illustrate the situation we have in mind. And so it tells us that Fn bar locally is below phi in the sense of the increments. So because Fn bar minus phi has a local maximum at Tn Hn, we also have that phi of Tn Hn plus H prime minus phi of Tn Hn is smaller than Fn bar of Tn Hn plus H prime minus Fn bar of Tn Hn. Okay, if you reorganize the terms here, you see the, yes, thanks for this other comment I forgot about here. Thanks a lot. I'm very happy that you catch my mistakes. Thanks for being attentive. Okay, so this is true because if you just move around the terms, you see that it means the said thing. Oh, except I did it the other way around. Sorry, phi is above. Wow. Okay, so I'm doing a couple of mistakes this morning. At the beginning of this session. Phi is above Fn bar. I did a drawing to not make the mistake, but still I did make the mistake. Okay, yeah, incidentally, I remind you as well that the drawing is, I do it like this because I want to remember which function is supposed to, may have some corners, but it's a bit misleading because Fn bar we know is convex. Okay, so it's not a very good drawing. So maybe instead of this drawing, I should draw it like this. Maybe phi is like here, and this is Fn bar. Okay, something like this. And the contact point would be here. Okay, and indeed the point is that because there is this contact point, we are showing that near the contact point, Fn bar must be regular in some sense. Okay, so where do I want to go with this? So now if I want, I can see. So okay, so one point I want to do first is I could write the same formula as here, except I would write phi instead of Fn bar everywhere. Okay, it's just Taylor's formula. It's insensitive to which function I'm using. The second point I want to make is that since Fn bar minus phi has a local maximum at this contact point, the derivatives will coincide. The dh of Fn bar or dh of phi at the contact point are the same. Okay, so on the left-hand side, there is an inequality between the case when I use Fn bar and the case where I use phi, okay, because of what we just wrote. And on the right-hand side, the first term, they coincide, whether I write Fn bar or phi. And so I would get an inequality between these last terms, whether I write Fn bar or phi, okay? So let's say combining these displays. And by this, I mean, including the display I have not written where you write phi everywhere. And the fact that these derivatives are the same. What do we get? Well, we get that, let me do it right. We get that the integral from 0 to h prime of h prime minus u dh2 Fn bar of Tn Hn plus u du is smaller than or equal to the same integral, but with Fn bar replaced by phi. Okay, and now phi is smooth. So it's clear that the integral on the right is bounded by a constant times h prime squared. Okay, the square comes from the fact that h prime minus u is at most h prime, and the length of the integral is at most is h prime. Okay, so this is bounded by some constant times h prime squared. Okay, the constant is allowed to depend on phi. And so now I know this, I can just go back one more time to this display on top of the screen. Oops, sorry about this. To the display on top of the screen, which is here. And now replace this integral by the bound we have just discovered. And this is exactly the estimate that I proposed that we prove. Okay, so let me display it one more time. What we wanted to prove is this. And so we have just gotten it. Okay. So now we have this. In particular, the second derivative is bounded. But yeah, I want to use this more refined form for later. See? Okay, so now let's turn to the thing we really want to control. So now we focus on estimating this derivative. Okay, and so this is where I'm going to also use that Fn is, I should say, semi-convex, if that talks to you. Anyway, the second derivative is bounded from below by something like which is kind of like a constant. So I'm going to say it like this. So for every h prime sufficiently small, we have that the second derivative of Fn at Tn Hn plus h prime is bounded from below by minus c and then the norm of z divided by square root of n. So if you remember at the very beginning of today's discussion, I recalled the estimate which had this 1 over h to the 3 halves involved. But here I'm focusing on a contact point which is strictly positive. Okay, h is strictly positive, and Hn converges to h. So if n is sufficiently large, Hn will be strictly positive and away from 0. For n sufficiently large, I can find some constant such that Hn is above this constant. Okay, and then if I also force this h prime to be not too large, I know that what I should put in this denominator here is not too small, and so I can just call it a constant, and I call it c. It's just to simplify a bit the notation. So I just have this constant z over square root of n. And so for this guy, when I try to understand this this Taylor expansion, I don't have a two-sided estimate, but at least I know that when I move by h prime, because it's almost convex, let's say I have that the function is above its tangent except for this quadratic correction. So this plus h prime th fn of th hn minus c h prime squared z over square root of n. Okay, so we're still inside the proof of the theorem, right? Because I'm trying to show this, okay? And for this, I need to control two terms: the second derivative and this concentration term. And in order to control this concentration term, I decompose the argument into two steps. The first step is to prove this estimate. And now we are facing this second step. Okay, now really trying to control this term in actual practice. Okay, just to answer the question in the chat. So I have this estimate. I'm going to use it. Maybe I could. Oh, I forgot a bar here again. I'm sorry. I'm seeing it. This was just. Okay, so I'm going to use it. But I'm also observing that I have some. Something of this sort that happens for Fn as well, which is on display here. I'm going to subtract the two terms. So I want to, because I want to use these estimates to control the difference between the derivatives, because they show up in both slots, in both inequalities. And I'm going to try to compute this difference by doing this sort of, I understand the concentration of Fn minus Fn bar, but I want to know something about the derivatives. And here I'm trying to approximate the derivatives by just doing a small increment. Okay. So what do I get if I compute this small increment in the derivatives? dfn minus dfn bar of tnhn. Well, I'm going to, Fn comes from this, and Fn bar comes from the same inequality for Fn bar. So what is on the, what should I put on the right-hand side of my inequality here? Well, there will be this, this Fn at Tn Hn plus H prime minus Fn here. And then minus the same things, but with Fn bar instead. Okay? Which come from the other inequality, which is no longer displayed. So I'll just bound this by 2 times the supremum of Fn minus Fn bar on some neighborhood I'm calling V. Okay, some neighborhood of Th, which we fix so that as n becomes large, all of these guys Tn, Hn, and Hn plus H prime will belong in this neighborhood. Okay, and there are the error terms. So there's this error term, and the error term from the other inequality, which was just C H prime squared. So what I collect here is C H prime squared 1 plus norm of Z divided by square root of n. Okay, and I'm hoping that from this estimate, I can extract the information that this guy is actually small. Okay, so let me say where V is some neighborhood of it doesn't need to be small. We can be very generous in the definition of TH. Okay, so this we know is true for any H prime in a small neighborhood. Like as soon as H prime is not too large, independently of n. So what do I want to do? I would like to take H prime to be aligned with this quantity, but it cannot be too large. So I'm going to choose. So let's choose for some. Let me say it like this. So for some lambda not too large to be fixed later, to be chosen, we fix H prime to be lambda times this difference of derivatives divided by the norm of this guy. Okay, this is always computed at TNH. Okay, so I'm going to plug in the estimate using this choice. Yes, exactly. So I'm catching up on what's happening in the chat, but thanks for being faster than me in answering the questions. Okay, so what happens when I plug in this choice of H prime? Well, I will get the norm of DHFN minus DHFN bar. This is really what I want to understand. Okay, there's a lambda. Is smaller than twice the supremum plus C lambda square 1 plus Z over N. Okay, and now I want to estimate the expectation of the square of the guy on the left. So let's square this expression and take the expectation. I will get lambda square, expectation of that guy, ups Fn minus Fn bar squared is smaller than, okay, so I'm going to put an 8 just to be on the safe side. And then here's the constant C is changed. No, maybe it's 2C now, but I'm just writing C. Lambda 4, expectation of, okay, let me write 2C. 1 plus Z over, oh, I forgot square. Square root of N, everything squared. Okay. And now on the right-hand side, we know how things behave. Right? This concentration thing tells us that this is bounded by C over N to the 1/3. And this guy, so Z square is the sum of squares of Gaussians. And they are just standard Gaussians. There are N of them. When we take the expectation, we just get N. And in the denominator, we had square root of N, which is squared, which is also N. So this whole thing in the expectation is just bounded by a constant. So I'm going to call plus C lambda to the 4. Okay, C is changing. All right, and now what remains to do is to just choose some lambda. So what lambda would I like to choose? So I guess N to the 1/6 would be nice. No, I'm going to take lambda to the 4 to be, so choose. I'm going to make it so that the two terms on the right-hand side are the same order. Okay, so that is lambda square is N to the minus 1/6. So I'm going to write this. Okay, so I would get N to the minus 1/3 on the right, but I have N to the minus 1/6 on the left. So ultimately, I get this. Okay, and now that's essentially the end of the proof now, because once I have this estimate, I can plug it into this approximate Hamilton-Jacobi equation we reviewed at the beginning, and then I let N go to infinity, and I get the result. So let's do this. So recall that dt Fn bar minus dH Fn bar squared is bounded by 1/n dH plus okay, this is what we reviewed at the beginning. And so if I compute this at the contact point, well, okay, first I can, if I want at the contact point, I can replace Fn bar by 5 because the derivatives coincide. And on the right-hand side, we said at the contact point, we observe that this guy is bounded by a constant. I'm going to write C over N. And we just observed as well that this guy is bounded by a constant divided by N to the 1/6. Okay, and now we let n go to infinity. We remember that phi is a smooth function, and we conclude. Other questions? So that's the end of the proof. And if there are no questions, then it's a good time for a little break. So let's take a 10-minute break. And of course, during the break, I'm always happy to have more questions as usual. So yeah, no, the concentration, I kind of subcontracted to the problem set. But yeah, I hope it's I try to decompose it in some step-by-step way, and I hope it's doable. I guess at some point, like there are people working on the overleaf documents, and they have been doing tremendously great work. So in particular, I would not be surprised if at some point someone writes a solution also in the overleaf documents. But yeah, if you haven't done it yet, I encourage you to check out what's going on in the overleaf documents. You can see it on the course website. Okay, so there are transcripts of what we talk about, and there are solutions to many exercises that are in the problem set. And if people find it, like sometimes I also write solutions. So maybe I will write solutions for this concentration if nothing happens in the overleaf document. Yes, so to answer the question in the chat, yeah, there's a bit of a manipulation you have to do. So when you go to the overleaf document, in fact, it's an overleaf project, and there are lots of LaTeX files. And when you arrive, I think the main file is lecture notes, and you see the transcript. But there are other files called SPS1, like a solution to problem set. SPS1, SPS2, etc. If you click on those and then you click on recompile, then you will see the solutions to the corresponding problems. Oh yeah, great question in the chat. Yeah, I forgot to point this out. We know also from this thing I record that this thing is non-negative. So just to try to have an overview of this proof one more time. In some sense, it's a little bit analogous to the sort of derivation we have done when we said that if we have functions that converge to some limit, and if the functions are convex, then at every point of differentiability, the derivatives will converge. And here the idea is very similar, because what we are doing is we're saying, oh, but look, at the contact point, in fact, okay, I would like to say C11, but if you don't like this language, let's just say C2 as a shorthand. At the contact point, essentially our functions are C2. And so if they converge in the pointwise sense, and if I have these particular places where the function is C2, then most probably I should be able to say something more. Like I should be able to say that the derivatives converge as well, because I can approximate the derivative by some finite order difference. So that's the gist of the proof. And in fact, for Fn itself, we only have a one-sided estimate on the second derivative, which is here. But this is sufficient, as we have seen. Okay, so yeah, let's recap one more time. So we have this. We start from this observation. We look at the contact point. We can observe that essentially it satisfies this quote-unquote C2 estimate at the contact point. Okay, it's as if the second derivative was bounded locally. Well, in fact, it is bounded. But we know that only exactly at the contact point. But this tells us that we can, in some sense, locally pretend that the second derivative is bounded even a little bit away from the contact point. And once we have this, we can express the difference between the derivatives as some finite difference question on Fn up to a small error. Yeah, an error which is of higher order. It's a square error compared with the other terms, which are of order 1. Okay, and then we just optimize and we get the result. Okay, and it's, yeah, that's what I want to say. All right, so what is missing now from this to our conclusion? There is one technical detail, which is that when we describe the the convex selection principle, it was for functions and equations that were defined on the entire read line. The H guy was defined in R, while here in this problem of statistical inference, we have restricted H to be non-negative. Okay, so I have to, the last bit that remains between us and the conclusion is to explain how to remove this technical annoyance, let's say. So let me say this. So to conclude with the convex selection principle. We need to address the fact that, oops. H to this non-negative interval. Okay, well, before it was ranging in R. And in fact, when we're doing this, so in this specific context, there's a cheap trick that allows to get rid of this problem, which is not available in general. So I'm going to comment for what we do in more general settings later. But for now, I'm just going to explain the cheap trick, which will allow to just complete the argument. So here we can simply solve this issue by just completing by symmetry. By reflection, we're going to extend the functions by saying that if H is negative, then we're going to set the function to be its value at the mirror image. Okay, so here we solve this easily by extending the function by a reflection. So I'm going to be more precise. So the main observation is that if so the thing that I should be worried about is so it's clear if so by reflection I mean f of th for general H will be defined by f of t absolute value of H, where this is the extension. And away from this H equals 0 place, the derivatives with respect to t will not change, and those with the derivative with respect to H will become minus the previous one. And so in terms of verifying that partial tf minus partial hf squared is equal to 0, this will still be valid for the reflection. The one point that should worry us is whether the convexity of the function will be preserved. It's not in general true that if I extend a convex function like this, I will get a convex function as a result. No, if you just imagine you have a linear function and you extend it by symmetry like this, this is no longer a convex function. Okay, and this is where the information of the function is non-decreasing is going to come up. Because if instead the function is non-decreasing and I extend it by symmetry, then it seems, at least on the drawing, that I will still get a convex function. So let me justify this. So let's say if f so r plus is 0 infinity, okay, closed. So r plus squared to r is convex and increasing in the second variable. I'm going to call it h. then this mapping is convex as well. Okay, so let's verify this. So indeed, or maybe I should say, in order to see this, we need to verify that for every alpha in 0, 1, t prime non-negative, and h prime in R, we have the convexity property, which is that f of alpha t plus 1 minus alpha t prime alpha h plus 1 minus alpha h prime. Okay, so I'm going to put absolute values everywhere. That this is always smaller than alpha f of t absolute value of h plus 1 minus alpha f of t prime absolute value of h prime. Okay, so I have to verify this. So I'm going to make so it will depend on the signs of h and h prime, and so I'm going to first reduce the number of possibilities by making a few observations. So first of all, yeah, if we change h and h prime to their opposites, then we don't really change the question. So nothing changes. Right, because there are absolute values everywhere. So without loss of generality, I can assume that at least the guy on the left side is non-negative. So we can assume okay, and also by symmetry, we may as well assume that h and h prime are ordered in some way. Otherwise, I can just exchange h and h prime. Okay, so now, well, if both h and h prime are non-negative, then the result is true because we assume f is convex. So there's nothing to do. So if h is non-negative, the result is clear. Now it cannot be that both are negative, or I should say non-positive. It cannot be that both are negative. No, I mean negative actually. It can be that both are negative because we have said that this convex combination is non-negative. So we must have the remaining case is h is non-positive and h prime is on the other side. Okay. And so in this case, yes, I'm going to say in this case, we need to say that so this is what I want to estimate. Okay, I assume that that the term here is non-negative, so I don't need to put absolute values. And I'm going to first use the information that the function is increasing in age. When I say increasing, I should say non-decreasing. I just dislike saying non-decreasing. But okay, I should say non-decreasing. So first I use this non-decreasing to replace age by its absolute value. Okay, so this is because f is non-decreasing. Okay, increasing. I go back and forth between saying one and the other. And then we can use convexity and we get the result. Okay, and h prime is a negative, so that does it. Well, I guess I could have. Yeah, anyway, that's the proof. Okay, so after we have done that, we can really come back to our convex selection principle and using the theorem we have just proved, the result comes out. So after this extension is performed, so what do we get? So again, I repeat, Fn bar, we know it's precompact. And now, using this convex selection principle, we know that any subsequential limit must be a viscosity solution of the equation that we talked about. We also know that the initial condition converges. In fact, it does not depend on n. So really, we have identified a unique possible limit for this sequence. And so we know it's convergent. So say the function Fn bar converges to the unique viscosity solution to this equation. Okay, so this is just by combining the convex selection principle with the theorem we proved in the first part of today's discussion. Okay, and by Hopf, or so in this case it's nice because we can use Hopf and Hopf-Flachs if we want. Okay, the initial condition is convex, but also the nonlinearity is convex, so we can use each of the two. We get that the limit as I'm going to of fn bar of th is equal to, where is this f of th, we wrote above, and is the supremum over h prime of, maybe I'm going to call this psi of h. So psi of h prime minus h prime minus h square over 40. Okay, so the convex dual of the square function is the square function over 4. And in fact, so when h is non-negative, it suffices to take the supremum, to take the sup over h prime non-negative. Okay, and now we are really we're essentially now it's downhill from here. Let's say now we have, you know, the harder part of the task claim was to identify the limit of the free energy. Now this is done, and now we can just play around with this formula for the limit and discover interesting properties. So, like with co-revise, we're going to observe that this function will have a phase transition as t varies. So for small t, at least locally near the origin, it looks like a parabola, and then ultimately it goes linearly. And for small t, this picture stays like this. And then at some point, the function will start to have a corner at h equals 0. And this will monitor the fact that this will monitor the transition from we are not able to recover basically anything on the X bar to we actually start to be able to recover something on the signal, the X bar. Okay, so let me write this down. So let's say like with co-revise, one can check that. Yeah, so I should say, so let's say that under the assumption that the, assuming that this data we try to discover, this X bar, let's say that it's centered. Otherwise, you can try to make some guesses which do something non-trivial by just proposing the expectation of this quantity. So it's a bit less nice to discuss, but there's still some transitions there. But okay, let's just say the prior is centered. Okay, this X bar is centered. One has psi of h is looking like a parabola near 0. And therefore, that there exists some critical t, which is positive and finite, such that so whenever if t is smaller than tc, then the derivative of f in h is 0. And if t is larger than tc, then this becomes positive. Okay, so in terms of the, and recall that th fn bar is 1 over n, the expectation of x dot x bar. Okay, so we're going to recover information about this quantity, which was the quantity appearing in the minimal mean square error. Yeah, so if you study there's a question in the chat about what happens when t equals tc, and in general it will depend on the specifics of psi. So if you choose a specific psi, then you're going to discover what happens one way or another. Okay. It can be positive or not. So concretely, this means that yeah, there's a region of signal to noise ratio. Like if we don't have enough, if the signal to noise ratio is not large enough, then we will not be able to recover any meaningful information about the signal. The minimal mean square error will be as large as if we just do the naive guess of deciding the signal is 0. Okay, so maybe said another way, for t smaller than tc, if I guess that the signal is 0, this is the best I can do. There is no better estimator around than just saying, oh, maybe x bar is 0. So it's not great. But as soon as t is above tc, then there are non-trivial estimators for the signal x bar. Okay, so we can find something, and in fact, the expectation, the conditional expectation is what does it. That has a non-trivial correlation with the original signal. And yes, and similar observations also hold for if I look at the t derivative, which encode more the minimal mean square error with respect to this x bar transpose. And so in problem set number 10, the idea is to play around this variational formula and see how it compares with an actual practical procedure for trying to recover the signal. Because in our conversation so far, we have focused on what is the optimal best estimator for the signal. We have not discussed whether this estimator is easy to compute or not. Okay, maybe computing the conditional expectation given the observation is actually extremely computationally difficult. So here, this result allows us to identify the region over which there exists an estimator that can recover the signal. But it doesn't say if it's hard or easy to do it. Yes. So indeed, so in this case, that's a good question in the chat about this addition of this parameter h. So for instance, here we see, I said at the beginning, I think at some point that in case the signal has some symmetry with respect to having a minus sign, then we'll always, the best estimator we can get for x bar is always going to be bad because we don't know if it's positive or negative. So when we add just a tiny bit of h, we are kind of breaking the symmetry, and suddenly it becomes possible, and we can do good recovery of the signal. It's one way to break the symmetry, and in practice, the way it's like for query vice, when we try to decide what's the magnetization at h equals 0, it's best to break the symmetry a little bit and add a little bit of h. So perhaps it would have been nicer if I discussed how it behaves as when we vary the t, because there the function will be differentiable for most values of t. So similarly, for the t derivative, I should say this is not exactly right. I should have said this is the derivative on the from the right side, because it has a corner there. So it's really like with query vice, there's a corner. But this is not so in general for the t derivative. And from this consideration of the examples with the symmetry, we see that it makes sense that there is a problem when we just try to compute what happens at 0 for this guy. So the T derivative allows us to recover the behavior of 1 over n square expectation of, let's say, XX transpose dot x bar transpose. Okay, and this is what appears when we think about the minimal mean square error, when we try to recover really the matrix, the x bar transpose. So in fact, in the problem set, this is the quantity we focus on. It's a more meaningful quantity, I believe. Really what we want to recover is what there is when there is no noise. It's this rank 1 matrix x bar transpose. Okay, and here, yeah, most points will be actually differentiable. So even at h equals 0, we can recover the limit in this way. Okay, does that make sense, the comments I said? Yes, so just to continue on what happens in problem set number 10. So in problem set number 10, we compare this theoretical result on what is the best possible approximation or way to recover the signal. We compare this with a specific procedure, which is this, let's call it principal component analysis, which amounts to looking at this observation and trying to compute what is the eigenvector associated with the top eigenvalue of this guy. I made a brief comment about this earlier during this week. And you don't have to solve this problem set, but I think it's interesting to see just what it says in terms of the question that it's asking. Because it's giving 3 examples using different laws on this prior, on this x bar. And for some of the cases, we have perfect matching between this algorithmically best possible way, information theoretic best possible way to recover a signal that we discussed during this class and the previous ones. And this practical procedure called PCA. So it's just, it just matches exactly the same. Like we have the same thresholds and the same minimal mean square error. There's a second example in which the thresholds coincide, so when it's impossible to recover the signal from this information theoretic perspective, PCA also fails, of course. And as soon as it's possible, principal component analysis will give us something. But in fact, there is a mismatch between how good PCA does and what would be optimally best. So we recover something exactly in the right region, but we don't recover quite as much as we could. And then there is a third example where there is actually a gap in which it is actually theoretically possible to recover information about the signal. But in fact, this particular technique, principal component analysis, completely fails to recover any meaningful information. So yeah, I think it's interesting to know that these 3 possible regimes are actually possible. We can find concrete examples where this happens. Okay, so one final comment I want to do is what happens when we consider more general models than the one we discuss here. Because I told you at the very beginning of this week that this approach that I discussed here based on the convex selection principle is particularly useful in these more general settings because this is basically the only way that is known to cover all the possible more general settings. And what will happen in these more general settings, as you perhaps expect, is that it will be more analogous to the generalized Curie-Weiss models. So here because of the convexity of the nonlinearity, we always had one inequality for free, right? I was writing this in our inequalities. Okay, so we have this inequality for free just by convexity. But in general, this will not be so. So in general, what we will have is, like with the generalized Curie-Weiss models, we will have only an estimate like this. Okay, and then the same terms, in fact. Okay, I should say, let me say in more general settings, there will be more variables than just one. And so the estimate will look more like something like this. So it will be some nonlinearity of the gradient. Oops. And then we'll have some estimate that involves the Laplacian of this function. And some estimate on the derivative of this function, on the concentration of this derivative. Okay, so structure very similar, but crucially, we have to worry about both sides now. And this is where this convex selection principle really shows its most usefulness. Yeah, last comment is that, so in this case, I did not describe yet exactly what is this extra variable. And in fact, it has to be a positive semi-definite matrix. So it's kind of, so the extra variable H becomes a positive semi-definite matrix. Okay, so I don't quite have time to explain what it is. So it's not obvious actually. But in particular, this reflection trick will no longer be available. You know, the way we said, so far we only deal with H non-negative, but we can easily solve this by doing the reflection. This will no longer be the case in this context. And so we have to actually deal with an equation in which there is a non-trivial boundary. So the variable does live in the cone of positive semi-definite matrices, and you do have to worry about what happens at the boundary. So it's not necessarily crazily hard, but okay, in practice, you have to think about it carefully. Let me think if I had other things to say. I think that's what I want to say. So that closes our chapter on statistical inference, and my goal for next week is then to turn to spin glasses. So thanks a lot for your attention, and as usual, I'm very happy to take questions. Yeah, so there's a question in the chat about how TC depends on the law of X bar. Well, you can find one bound on TC if you know that this initial condition is bounded by a constant times H square, then you can do this using the comparison principle. You can find a bound for TC. We know that TC is below something. And not always, but oftentimes, this will give you a pretty good prediction for what TC is. And this C, near H equals 0, the behavior is prescribed by the second moment of X bar 1. So in some sense, at least as a first guess, you should think that TC is basically the inverse of the second moment of X bar. But in practice, things are more subtle because sometimes the singularity starts to occur because of the behavior of this initial condition far away from the origin. So it's a nice rule of thumb, but there are some subtleties. So down the road, you have to analyze the variational problem.